We conclude the durability part by discussing the effect of the loading conditions, namely fatigue and creep. So this is the second part of the durability section, where we are going to talk about the loading conditions, in particular fatigue and creep. So starting with fatigue, in reality the spectrum might be highly irregular, but in the laboratory ambient we tend to use regular cycles where the average, amplitude, etc. Of the stress applied is very well controlled. We have basically two approaches to design in terms of fatigue. The first one is to use the total fatigue SN approach, S for strain, N for number of cycles. And within that approach, within the SN approach, we have two different alternatives. We have the direct one and the indirect one. Direct one consists in doing fatigue tests on joints which are very, very close to the real joints. We apply different stress levels and we generate the SN curve such as the one indicated here, and with this tool we can, for a particular stress level, know what will be the number of cycles that the structure can withstand. The other approach, the indirect one, is to use simpler specimens, laboratory specimens, where the geometry varies, the type of loading varies, and of course we'll have different SN curve generated. But you can collapse these stress N curves into one master curve if you define an effective stress. This effective stress will take into account precisely all the stress levels and the change of geometry, and will generate a master curve where you have effective stress versus number of cycles. With this master curve, you can go to the real structure, determine with an elastic analysis the effective stress, and then determine the corresponding number of cycles. Of course, you know that the SN curve will change as a function of temperature and humidity level, and will go following this trend. The strength, of course, the fatigue strength will decrease. The other approach for fatigue design is to use the crack growth approach, using the Paris law. You have here the crack growth rate versus the strain energy release rate. You have a threshold region, you have a region where you have unstable crack growth, and you have a stable crack growth region where the Paris law is valid. With this Paris law determined in fracture mechanics texts, such as the DCB, double cantilever beam test, you can predict by integration the number of cycles that the structure can withstand before it reaches the critical crack length. This is what is being described in these equations. First, you determine the critical crack length with the toughness of the adhesive, and then by integration of the Paris law, you can determine how many cycles the structure can withstand. In the case of aeronautical applications, you can determine how many flights the plane can withstand before the crack reaches the critical crack length for which there is unstable crack propagation. Again, the Paris law will vary as a function of temperature, mode mixity, and humidity level. Humidity and temperature will increase the crack growth rate, and the mode of loading is also very important. Mode 1 is much more severe than mode 2, so again this goes in line with the philosophy of adhesive joint design, which says that you should load in mode 2 as much as possible, or in shear as much as possible. Regarding creep might be a problem for adhesive, especially if you are at a temperature that is relatively close to TG. In that case, for a constant load applied, the deformation will increase. If you want to design for creep, then you need to generate the creep curve. You already probably know that. In the creep curve, the most important parameters, so creep curve, you have the strain versus time. The most important part is the steady creep curve, and you will use that for design or the time to failure.
Today I'm going to show you a testing creep machine that was developed to test pressure-sensitive adhesives, or PSAs. This is a device that is based on a lever mechanism, as you can see here, where we put the weight on this side, and then your joint is going to be loaded on this side. To measure the displacements that we need for the final curve, we use a LVDT, a linear transducer, that is going to acquire the different voltage that is going to occur during the test, and in the end we can obtain the creep curve that we want, that is strain as a function of time. This particular device was developed for a project where we test PSAs for applications in electronics.
Again, the creep curve will vary a lot with the stress applied, if the humidity is high or the temperature is high, and it will go in that direction, the trend. To generate creep data is very complicated because it takes a lot of time. So in general, we use a lot of several devices that can generate many curves at the same time. One of the devices that is used is this simple device, just a weight, and you need a dial to measure during the test the displacement of the joint, and you can put this easily into an oven. Another apparatus that is quite common is to use a spring which apply a constant load. A dial is also used to measure the displacement of the joint. In this case it's a bulk, but you can use also a single up joint or another kind of joint. Another test that is used in the creep contest is the relaxation test. In this case, you don't maintain the load constant during the test. You maintain a displacement, and you are going to measure the relaxation in terms of stress, which is what is indicated here in this graph, load versus time to failure. In talking about relaxation, this is very important and has a big impact in the constitutive models that are used for the adhesive. If you are at a temperature that is well below TG, you don't really need to worry about relaxation problems. And just a Hookean spring will be enough because the relaxation time is way higher than the time stress applied. You have an instantaneous response in terms of strain. Now, if you are close to TG, the relaxation time is comparable to time stress applied. And if you apply a stress, the strain will take some time to reach the maximum value. For the constitutive law, you need to apply not only a spring, but also a dashpot. So that's for the durability, and in this module we concentrated in fatigue and creep.
And that concludes the course. You have now an introduction to the technology. You know how to select an adhesive, how to design a joint, how to fabricate a joint, the precautions you should have when handling an adhesive, and the issues associated to durability like temperature, water, fatigue, creep. I hope you will use this technology in everyday life or even research this technology. In that case, our lab is open and you are more than welcome. Bye-bye.